Good afternoon. Can you hear me okay?
Yes.
Great, thank you. Thanks. Yeah, welcome. This is the 17th now in our series of webinars. And today we're very pleased to have with us Professor Mark Mulligan from King's College London. Mark's going to talk about developing and deploying a low-cost distributed monitoring system to evaluate the effectiveness of NFM. Hi, I'm Gerard Stewart. I'm the communications coordinator for the NFM research program, and I've just got a couple of housekeeping things to go through and a brief overview of the research program before I hand over to Mark. Please, could you keep your cameras and microphones switched off to avoid distractions during the presentation. If you do have questions or comments, please do use the chat. We've had some really interesting discussions going on during the webinars, so yeah, please do use that function, and there will be time for Mark to answer some questions at the end, hopefully 10 to 15 minutes. I am recording the webinar and I'll make this available on our website shortly after we finish, and I need to let you know that as well for GDPR purposes. So the NFM research programme, it's a 4-year, £4 million programme, and we're carrying out novel science to improve understanding of NFM where possible, including quantification. We're looking at a range of measures in different types of catchments, flooding scenarios, and at different scales. And our aim is to improve evidence and understanding for policymakers and practitioners. There are 3 projects that make up the programme, working closely together, but each focusing on different aspects of NFM and working in different geographical areas of the country. So drawing on the expertise of partners and engaging them in our work is critical to the success of the research, and this webinar programme is part of that engagement. Today, Mark, he's not directly involved with our research, but he's an important member of the NFM community, if you like, and the aim of one of the aims of the webinar programme is to build and share experience within that NFM community. So yeah, this is gives you a flavour of the range and number of partners that we're working with as part of the research, a very important part of our work. Okay, I think that's enough from me. Time to hand over to Mark. Over to you, Mark.
Okay, thank you very much, Gerard. I'm just gonna share my screen now, and thank you all for coming. As always, this is a collective effort of a number of people that you see here in the pictures. Arnout, Sophia and Caitlin in particular, looking tidy in the lab and less tidy in the field. So as you heard, we're going to talk about low-cost sensing and its role in being able to deploy over large areas to better understand NFM. So I'm going to talk about the problem to start with, and then the development of low-cost do-it-yourself monitoring solutions as a solution. I'm going to show you some deployments around the country in leaky dams, retention ponds, and regenerative agriculture. We're going to talk about some of the challenges and the practicalities of building and deploying your own kit. Talk about some of the findings that we have so far. We're still analysing the data. And then I'm going to give you a heads up on how you can begin to build your own, should you be interested to do so. So first of all, the problem, of course, is that each natural flood management intervention is different. Leaky dams, retention ponds, and soil management regimes vary in their design and in their scale, so they can be expected to behave differently. And secondly, the geographical context for these interventions is everything in determining how they actually behave. So our approach has been, rather than focus in on one site and look at it in great detail, to deploy monitoring over a range of sites in a number of catchments extensively rather than intensively. But the problem with that is that monitoring is expensive, both in the specialist equipment and the sensors that you need. And if you have them across a range of sites, particularly in relatively densely populated areas, they are vulnerable. The associated infrastructure that you might need, such as weirs and other flow control structures, are also expensive. And of course, the time that it takes to visit, collect and analyze data from lots of sites can be expensive. And that's why, building on work that we had done in previous projects since 2014, we developed these network connected low cost DIY sensors and automatic sort of and analytical tools on the web, so that we could basically scale this up without the cost and without the risk of expensive commercial equipment. We monitored sites on 13 rivers that you can see listed there, and we built and deployed 101 free station loggers, collecting in 2020 more than 21 million readings. And that was, of course, despite the lockdowns, which prevented us from getting to the equipment sometimes. Many of these loggers are still collecting data, and the analysis is ongoing. So FreeStation as a technology is a response to the declining ground-based infrastructure for monitoring globally. You can see that very clearly in the precipitation stations that are sufficient quality to make it into global data sets. They are declining over time, as you see here. And that's a problem. It's partly because of governments spending less money on monitoring. It's partly because of greater reliance on remote sensing and other things. But on the other hand, the technological barriers to designing and building your own hardware are falling. And so many more can get involved in monitoring than was previously possible. And with FreeStation, this is environmental monitoring with open source DIY hardware since 2014. It works out around 3% the parts cost of the equivalent proprietary equipment. It allows us to deploy many more loggers with the same amount of money. It's web connected so that it can be utilized in nowcasting, integrated with models and kept an eye on. And whilst there are many low-cost sensing projects out there, this one is designed not for electronic engineers to engage with, but actually for geography students to engage with. So it's relatively easy to build from these designs. We have a variety of instruments, all of which are good enough for the job, not perfect, but good enough for the job. They are designed with consumer, off-the-shelf, and thus cheap components. All the parts can be plugged in and out, and so are replaceable when they wear out. And all the stations can be reconfigured from one station type to another. So it could be a weather station one year, and then it could be a stage logger another year. And they're easy to build, easy to ship, and easy to install. We have collected quite a lot of data so far with this technology. We started in 2014, but we only started monitoring how much data was coming in 2019. And you can see the number of records then. Over the last couple of years, we built a series of online tools that help us to better manage and analyze the data streams that are coming in. Now, it's important to say that low cost doesn't necessarily mean low accuracy, precision, or quality. Low cost means that we are using non-specialist, consumer, mass-produced parts and our own labor. And these parts are often the same parts that are used in commercial systems, but because monitoring of the environment is pervasive in various types of technology now, including, for example, washing machines, mobile phones, etc., etc. These components are readily available. And here is just some example data. I don't, of course, expect you to read this, but you'll have the slides later, where we compare free stations with commercial stations. We are usually, very close, within half a degree of temperature, within 2 or 6% of humidity, depending on whether you want to spend £2 or £5 on the sensor, within a centimetre of stage, and we're also within 5 watts per meter squared of solar radiation, with very low coefficients of variation between replicates and so on. And since the components can be cheaply and easily replaced, then if instruments go out of calibration, you don't recalibrate them, you just replace the part. And that makes things a lot easier. So here are some basic stations. We started off back in 2014 using a microcontroller to power these stations called an Arduino. That is good, but it has its limits. And so in the last, certainly the last 3 years, we've worked with particle microcontrollers, in particular the Photon, which is Wi-Fi enabled, and the Electron, which is GSM enabled, so connects to mobile phone networks. And we build 2 types of loggers. We build local loggers, which don't connect to the phone network, and you have to go to them with a device to download the data via Wi-Fi locally, and the Wi-Fi goes through your mobile phone, or the live loggers, where they are continuously every hour sending data along the mobile phone network. And you see a soil moisture sensor here in a field. This is a stage sensor, and then a couple of weather stations. Here are some others. Here's another stage sensor. This is our easiest build, which is a classroom demo of water quality, prototypes, pole photography, if you don't have a drone, rainfall and soil moisture weather station here. And then this one is used very heavily in our NFM work. This is a free station scanning LiDAR that allows us to better understand the profiles of small rivers and streams, again, at very low cost. So the limitations of the Arduinos are largely that they have very low processor memory and program memory, and that means that you can't do very sophisticated things with them because of that limitation. But also the problem with them is that they don't have what's called a watchdog. And a microprocessor with a watchdog, if it fails, it reboots itself and restarts. Arduinos don't have a watchdog, so if they fail, that's it. And you have to go and reset it to restart it. So those are some of those limitations. Here are our key deployments. We had a lot going on in the Blackwater at Spain's Hall, where there are leaky dams and beaver reintroduction, leaky dams at Bishop's Wood, retention ponds on the Mole, leaky dams in the Stour, Mardyke and the Leck, and some regenerative agriculture work at Lanark Manor Farm and a bunch of other farms too. Okay, so I'll talk about theft and vandalism shortly, and we've had a little bit of that, but not very much. We distinguish between these 2 types of NFM at a point NFM, things like retention ponds, beaver dams, leaky dams, where they're occupying a small space at a point, and then retention of water over much larger areas, aerial NFMs, such as good soil management, including conservation or regenerative agriculture. And if we start off with some of the point interventions, these are some example deployments of our stage sensors. Our stage sensors are perhaps the most common deployments that we've made. They use a car parking sensor, which is a very low cost of the order of £5, sonar sensor, to bounce a sonar every 10 minutes off the water And of course, with temperature and humidity and air pressure also measured, we can know the exact distance between the sonar and the water, and thus the stage. These are non-intrusive, they're easy to deploy, as you see, and we can either put them either side of a dam to understand the difference the dam is making, the behavior of the dam, or we can put them either side of a run of dams, or either side of a run of dams and downstream at the asset at risk. In each case, we would use the LiDAR that we build for about £180 to measure the profile of the channel in order to be able to convert the stage to a cross-sectional area and thus volume of water, getting a kind of stage volume diagram for each site. This is Spain's Hall, where there are a whole series of leaky dams, but also beaver reintroduction. And again, we've got either side of a dam to try and understand the difference in height, but also here we're measuring the velocity of the water either side of a dam. Here's how we've measured velocity to date. I have to tell you it's not very good, but it was a reasonable start. We have on the free stations a couple of low-cost model boat propellers that turn and are calibrated with speed of the water. They do, of course, in these muddy little ditches tend to attract reeds and clog up quickly. So we are now moving to another system which is slightly more sophisticated based on differences in pressure. Sometimes we deploy the sonars above the water, as you see here, so as not to have a pole in the water that can trap reeds and so on. But sometimes where we're dealing with different situations, we simply have a pole in the water. So here's a variety of other deployments, and again, in each case, we measure the profile. In terms of problems, any of you that do fieldwork know that fieldwork always has problems. The kinds of things that, of course, challenge us and that we learn from are shown here. Of course, if you have a pole in the middle of a river, when the river is high, then all sorts of trash is brought down from upstream and that builds up. We therefore learn very quickly not to have the sonar on the upstream end, but on the downstream end, because of course here we're not measuring the water height anymore, we're measuring bits of wood, bits of timber, but on the downstream we wouldn't have that issue. Indeed, on this one we replaced it with an elevated station like this here. The other problem you overcome is you don't realize how powerful these rivers are when they are in spate, and we've had some big storms recently. So at Spain's Hall, this station obviously was a great trap for weeds coming down and other trash, and that pushed it over. And then the same here, this one, the water came up so high, much higher than we expected, that again washed it over. Surprisingly, you know, although this had been underwater, these two hadn't, it was still fine. You know, it had stopped recording because it was no longer getting solar power, but it wasn't damaged. So you get the build-up of trash, you get vegetation growth as well that can get in the way of the sonar, so you've got to ensure to keep that back. You have problems of shade with lots of these small streams. They're very shaded in woodlands and so on, and that can be problematic for solar power. Ditches aren't great places to get mobile signals, particularly on 2 and 3G, and so we often have to put masts up with these stations to elevate the aerial above the ground. The force of water can be important, and then occasionally there is vandalism. We don't see too much of a problem with vandalism. Out of 110 loggers, we've only had 2 instances, one where a logger was stolen and ended up, it seems, in somebody's house, and then the other where someone tried to make away with the solar panel, which is the only bit that is vaguely useful. Clearly they didn't manage that because it's all screwed down, but it caused some damage. Of course, to avoid these problems, we label the devices. That's important anyway, so people aren't suspicious of them, you know, what they are, what they're doing, the fact that they're low cost and volunteer made. And we work with local people. We try and put them out of sight. We don't put them next to paths if possible. And in some cases, we disguise them. In shaded locations, it really depends. If you're using a free station local, which doesn't send over the telephone network, then in shaded locations, they can run indefinitely on batteries with a solar panel. It depends on the intensity of shade, but we certainly have plenty that are running fine in woodland now. The live devices that connect to the phone network require a lot more power to send data 30 kilometers to the nearest mast. We have some of those in shaded locations as well, but do tend to cut back the shade a bit to ensure that the panels receive enough light. Or now we also double up the number of solar panels. So point interventions are great. They can be monitored, and we'll look at some of the results later. But if we look at where most of the water storage is in the UK, and these are results from our Water World analysis, a model that uses remote sensing data to estimate flood storage, we can see that, you know, water bodies and floodplains and wetlands don't hold huge amounts of storage at the national scale because they are intermittent. They're here and there. They're not everywhere. The big stores at the national scale are soil and canopies where they exist. And so better management of soil, in particular, can do a great deal to mitigate floods downstream. So we've been doing a lot of work also on farmland, looking at conservation or regenerative agriculture. Ploughing is, of course, an established technology for weed control, largely. However, its long-term use has serious impacts on soil organic matter by turning it over, exposing it to the atmosphere, oxidizing it, on soil structure, on infiltration rates, and on the volume of water stored in soil. Regenerative agriculture is many things, but some of the things that are often done is the reduction or complete halt in the use of the plough, and either plant weed-resistant crops or control weeds through other techniques, drilling them in the process rather than turning over the soil. We have found that this significantly increases soil storage for water, which can have benefits in flood mitigation, but also in avoiding dry season drought risk. And since this can be implemented over very large areas, because farmland is most of the UK, it can have significant impact at relatively low cost compared with very highly manual point scale interventions. In some cases, regenerative agriculture is cheaper for the farmer because there's less equipment, less fuel, and so on. But there are, in the first few years, costs and risks of transitioning. And not all land, of course, behaves in the same way. So, you know, moving over to regenerative agriculture doesn't guarantee natural flood management benefits. Where we're working on farms, we tend to have this kind of deployment. We have a trench with a whole series of moisture meters, low-cost soil moisture meters, or an isolated area with the soil moisture meters around the free station. You can see it's aerial here. And we tend to work where there is a farm practicing regenerative agriculture, and then in the next field, a farm with conventional tillage. So you can see that here. We have the regenerative field, we have the conventional tillage field. We put the free stations at the edge of the field so that we don't have to take them out when the farmer comes to harvest the crops and so on. But then we dig a trench into the field, and the sensors go into the field where the management is properly representative of regenerative or conventional. On farms, we have particular problems with animals. All sensors need to be protected against wildlife. Where we've worked overseas, you can see here, not good news. We may have lost the depth sensor to a crocodile. This was in Burkina Faso. Of course, the animals that we have to cope with in a UK context are somewhat cuter than crocodiles, but just as nasty if you are interested in keeping high quality data. The impact of a rabbit or a hare on your data set is something like this. You know, we're collecting good data on soil moisture. Rabbit comes along, as you know, they like to chew cables, and then everything goes haywire. So we tend to cover everything, as you saw in the last picture, with conduit to avoid that. In terms of thinking about some of the findings, you can see that leaky dams can work if they're done well, and this is a good example from the Stour. These at-a-point natural flood management techniques can be effective if the assets at risk of flood are nearby downstream, or if these dams activate flood meadows. But otherwise, of course, we're talking about small volumes that are retained behind these dams. Nevertheless, where you have a number of them, they can be impactful. Here we have a free station upstream of a set of 11 dams on the Stour, that's the red line, and downstream of those 11 dams on the Stour, the orange line, and you can see that the dams are reducing the peak, and this is discharge rather than stage, so reducing the peak and increasing the recession, both in terms of the height and the duration of the recession. So these are doing what we would expect them to do, and the difference here is about 25% in the peak, so that's significant. But this is a small ditch, small stream, and although there are many dams in this area, 272, if we look at how much of the catchment of Shipston on Stour, they actually affect 2% that set, 1% that set, 2% that set, 1% that set, etc. We're only covering a small fraction of the catchment of the asset at risk, and nearly 85% of the catchment is still unmitigated or has no intervention associated, even though, of course, this is a huge body of work. So they can be, they're doing what they're supposed to do, but scaling is the challenge. Here are some of the results from Spain's Hall, where the village of Finchingfield here floods fairly frequently. There's a number of reasons for that. We're at the junction of 3 streams, and the properties around the village pond flood every few years. Most of the land upstream is owned by a single landowner, Archie Ruggles Bryce, and he's tested a whole series of interventions, including the reintroduction of Eurasian beaver in an enclosure, and these beavers have built, I think, more than 20 dams now, and a whole series of very, very significant leaky log dams along the main stream that you see here, again with a couple of free stations in. So this is the setup of our sampling there. We have, the stream here that is the beaver stream. We have the stream here that has the leaky dams. And then we have the east stream here that has no mitigation. It's a different landowner. And we have estimated the catchment contributions. 75% comes down the main stem, some 11% comes down the beaver stream, and 13 or 14 on the east stream. And we're measuring either side of dams, we're measuring either side of the beavers, we're monitoring the volume within the beaver pound, and we're looking at the differences also downstream, as well as, of course, having an automatic weather station or two to keep an eye on the weather. What we see with the beavers is that, of course, they can make a contribution. Beaver dams are not so leaky as human-made dams, partly because they use mud like this to bind everything together, and also because they're pretty good at repairing after rainfall events. There are many co-benefits, of course, for biodiversity, habitat, etc., in the creation of wetlands. And interestingly, in monitoring these beaver pounds over time, this was a very rainy January, we see that even though these pounds may be full after the first rainfall events, they tend to build them up and build them up and build them up after each rainfall event, and so the volume of storage increases and increases. And in the almost 2 years, I think, that they have been in place, they have converted a single narrow channel, like some of the ones I showed you in the picture, to a complete wetland, as you see here in this area of woodland. And with these live sensors, one of the things we're able to do is to monitor, and you can click on the website now and get an estimate of roughly how much water they are holding back. Here are the leaky dams at Spain's Hall, and you see our sensors in either side during an event here, photo by Archie, and you can see that the dams are very effective, not just in storing some water behind the dams, although that's a small amount of water, and in slowing the flow to an extent. What they're really doing here is activating the floodplain, lifting the water just by enough so it spills out over the floodplain. That's good design. We don't end up changing the flow pattern of the river very much. It still goes up very quickly and down very quickly. Right? So we're not doing a great deal in terms of avoiding that strong peak, but what we are doing is spreading the water out to activate the floodplain. So the free station that we've got on the floodplain here shows, okay, there's a peak of water that coincides with that event, and you can see that more clearly in this drone photo, where the whole of this floodplain is activated. There are a whole suite of leaky dams down here that have helped to achieve that during that wet period that we had this year around the 14th of January. There are challenges with point interventions, of course. Leaky dams and retention ponds are difficult and expensive to build. They require maintenance, particularly after extreme events. They clog up with trash and become less leaky and more vulnerable to failure. You can see that, I think this is the Lek, where we have a leaky dam here, which was formerly upright, has captured a huge amount of vegetation and has been pushed over by the flow, and now, of course, it is vulnerable to being washed away, as you see with the gap here. This one at Spain's Hall, where it's over a whole series of events, it's being undermined at one end and will need some repair work. Some designs are better than others, and of course designs must be adjusted for the hydrological setting. But the big problem with leaky dams and retention ponds is that scaling these to be significant for larger rivers is hugely expensive in both capital and recurrent costs. So whereas some other techniques are more scalable. So what does failure look like? Well, this isn't a complete failure. These timbers have not moved downstream yet, but it is, of course, possible in the next large event that these will start to wash downstream. And where you have leaky dams on the edges of urban areas, that can, of course, be a risk to culverts and to other grey infrastructure, and make the situation more challenging downstream. So we do have to be aware that if we're investing in interventions like this that are in channels, we have to think about the maintenance costs in the long term. With regenerative agriculture, here's some results from two fields next to each other. This one is under regenerative agriculture. We know that from measurements it has much more carbon-rich soil because of that. It's better drainage because of all the organic matter And this is the neighbouring field, same soil and geology, but without the enrichment by organic matter that results from stopping the plough. And you can see that on the one hand, the regenerative agriculture soil retains a lower soil moisture to start with because it drains better, so that when the rainfall event comes, it takes up some of that water, the soil moisture increases and then slowly drains away. Whereas for the same event in the neighbouring field, well, it's already wet to start with because it's effectively got more clay and less organic matter, so it's not draining so well, and so there was very little capacity to uptake water. All that rainfall that fell on this field will run off straight into the ditches and streams. So this can be significant if we're talking about large areas of land, because the volumes of water that we can store over fields the size of which we have in the UK is really very significant. But unfortunately, the effect is not consistent. We don't see that same effect at every site. So here we have a regenerative agriculture on one field, and at the neighbouring field, again, conventional tillage, the rainfall's going through, and we don't see the same pattern. Now, this has only been under zero till for 3 years, so maybe it takes a lot longer for zero till and regenerative practices to have a significant impact. And we have noticed at other sites as well, where there are particular layers in the soil, sandy layers or other structural features of the soil, they can mess up the pattern. Even after 3 years, we have more organic matter, but we don't have the hydrological effect yet. So, those are some basic findings. I should also say that, as you all know, assessing the impact of natural flood management is challenging. There's often no baseline or counterfactual to compare with the pre-NFM once you put the NFM measures in place. Estimating discharge is difficult without building flow control structures, and that's not possible in many rivers and across many sites. NFM also stores water below ground, and that needs to be measured. So even when we're looking at leaky dams, we also measure the underground moisture near them, because not all of the storage is above ground. Most of the time when you have equipment deployed in the field over many years, you're just measuring flat lines. You only really get interesting data during big storms, and of course the equipment is at risk then. And of course, if we're comparing flows upstream and downstream of a network of dams, we are subject to the impact of side flows that can affect our data. Whilst comparing either side of a single dam doesn't help us to understand the impact of a network of dams. So we need to do both of those and to do them carefully. Retention ponds, and especially beaver pounds, are bathymetrically complex. Their volume is not easy to measure from their depth, and so that is also a challenge. And each dam in each location that we have worked at seems to behave differently. So extrapolation of the impact of these features is challenging. It's not impossible, but it is subject to error. So I'll just spend the last few minutes talking about how you can get involved in doing this kind of thing if it's of interest. On the one hand, you can set up your own monitoring system relatively easily. You need a printed circuit board, which is our FreeStation design, and that's what all the components get added to, and that is really the heart of this. You need a microprocessor, Arduino or Particle. You need an SD card module, which stores data locally, even if your device is connected to the telephone network. That does go down. You need local storage until it's back up again. You need a real-time clock, some kind of human interface device so that you can see what the system is doing, usually a small screen or a multicolor LED we use for the device to tell us what it's doing. You need a series of connectors. We use Ethernet cables and phone cables as robust and easy connectors, and you need sensors as well as a housing and some batteries. So these are the basic components. The FreeStation website has a bill of materials that allows you to source all of these on eBay. What can you build? Well, you can build weather stations, soil moisture and drainage loggers, water quality loggers, although they're at the moment still prototypes stage, etc. And a wide range of other things can be measured. How do you start? You go to the building part of the website, and that takes you through the building of the sensor, the putting together the microcontroller, the upload of the firmware, attachment of batteries, development of the housing, and it's step by step like this, text and images on how to build. What do you need? Not much. A simple bench, a few tools, these sorts of things here, most of which you will probably have. Soldering iron, steady hands, safety gloves, and protective glasses, because you are dealing with sharp, hot things. You need to be able to follow the instructions, of course, and you need to recognize that if it doesn't work when you put it together, then you've done something wrong. We've built, probably nearly 300 of these ourselves, and so they do work, and you have to have this modular, it stopped working when I did that, so let's take that out and try it without that to see if that is the problem. Once you are collecting data, our smart system is where that data ends up, and that provides you with the ability to look at the data, download the data, look at the data relative to a global weather forecast model, so we can look at the data that we've measured, but also the prediction over the next few days. This is for Spain's haul. And there are a variety of NFM relevant analyses that can be done in that, and I'll go through these very quickly because I'm almost out of time. We have an analytical tool. If you have a deployment either side of a dam like this, it will allow you to put in the number of your free station. Each free station has an L number, and you'll be given one when your free station first talks to our servers. That will allow you to plot the two lines of a discharge or stage either side of the dam, as you can see here, the upstream and the downstream, and to calculate the difference. That's what that does. This is for inline storage. It allows you to calculate with the area of the water body and some assumptions about its shape from the stage data. You can calculate the volume of water and the proportion of flow at a downstream asset at risk that volume represents. So this retention pond here, compared with a downstream flow of 1 cubic in a stream just downstream of it, is only 0.25% of that. Oops. And then the third tool that is NFM relevant is to do with regenerative agriculture. It does a similar thing to what we just described. You need to put in your station number, and then it will plot your regenerative agriculture next to the counterfactual station in the field next door. So you have two station numbers, and it will calculate the volume of that storage in relation to a discharge downstream at an asset at risk that you either specify in cubic meters per second or that you actually measure from a free station downstream. This, of course, is all only important if we consider where the assets at risk are in relation to where your natural flood management is. We have a tool for that called EcoActuary, which is a flood risk catastrophe model that spends particular focus on mitigation by natural infrastructure. And here's a few maps from that. Floodplains. This is the total damage cost on floodplains downstream of each pixel. So, of course, if we're upstream of Oxford and Reading and London, then potential damages are very high. And this one factors in where the green infrastructure is to indicate that although these areas are important in terms of the volume of assets downstream, they are actually quite far away. And it's green infrastructure here, right around London, that's more important. So I've said that different types of NFM have different impacts that depend on their design and local context. Point scale NFM will have to be really common in the landscape to have a meaningful impact on significant rivers and streams, though it's fine if your asset at risk is just downstream, as in the case of Spain's Hall and Finchingfield. Aerial NFM, like good soil management, scale much more readily. Low-cost DIY sensing can help in a variety of ways, by measuring storages directly or as a proportion of water volumes and assets at risk downstream. It's not without challenges. Building and deploying equipment never is. But with low-cost equipment, it's low financial risk. And the fact that you can replicate, do many, begets resilience. So that if some are washed away or fail in other ways, you still have others. So that's all I have for you, just to say that if you're interested in further courses on FreeStation, we will have some coming up through our EU project called Reset. So follow me and you'll find out about those. We have one with the RGS coming up out on the Thames Estuary, hopefully in May, if the restrictions allow. Thank you very much.
Thanks, Mark. Very interesting. Some great pictures as well. Brought it to light, to life. Had a lively chat, and Dr. Caitlin Douglas, who's working with you, has been answering a lot of the questions, as you may well have seen. Thanks to those of you as well who submitted questions beforehand. Perhaps if I kick off with one of those. Yeah, I was impressed with your use of car reversing sensors and model boat propellers. Very inventive. But what have been the challenges in the design of these sensors and systems?
Yeah, I think the challenges in design are very different to the challenges in deployment. You know, where a sensor system has already been designed and well tested and so on, as our sensors now have, for example, the stage sensor, I think that the challenges are low. But for us in the design of them, you know, on the one hand, we're trying to collect good quality scientific data. On the other hand, we're dealing with prototype software, prototype hardware, and so on. So that requires a lot of testing in the lab and calibration and testing, you know, in back gardens and things like that, before we send these things further afield. And the big challenges we had certainly in 2019 was developing firmware that was resilient to UK mobile phone networks, which in rural areas are surprisingly poor, particularly 2G and 3G, and so fall over all the time. And of course, you need the sensors to be resilient to that, so they don't keep trying to send data, because then they'll run out of battery. They recognize that the phone network is down, and they hold off until they can find it back up again. That lost us quite a bit of data in places like Kent, where signals were very poor.
Okay, thank you. And how difficult is it to build a free station?
I think, you know, they're designed to be built by geography students.
Okay. And how frequent should water level readings be taken? I'm not sure if that's me who's frozen or Mark.
No, I can still hear you.
I think it's Mark. I think he's.
Oh, okay. Thank you.
Guess he didn't like the question.
Can you hear me now?
Yeah, great. Hi, we can hear you again.
Sorry.
Yeah.
So I was just saying they're designed to be built by geography students. So you know, anybody with more of a sort of engineering background than that will find it easy. We have done the difficult bits so that if they really are quite plug and play now. you still need to know how to solder. If you don't know how to solder, you're not going to get anywhere.
Okay, thank you. And yeah, as you said, you're running courses to help people as well. There was a question about scrolling through a list of questions. Oh, sorry, where's it gone? Sorry, well, I'll ask you another one of the submitted ones while I find it. What are your plans for developing flow sensors and for further development of the level sensors?
Okay, so with the level sensors, I mentioned that one of the issues is that where you have streams that tend to get very reedy, that the sonar sensors aren't very good, because as soon as reeds start to grow beneath them, then of course you get multiple reflections from the sonars, and it's no good. So we have a variety of pressure-based sensors that we're prototyping now. Many of them are out in the field at Spain's Hall and are collecting data, and also on the Stour, but they need a bit more work to get them properly calibrated against temperature changes. In terms of flow, we have some designs that are back with the propellers, but with screens in front to prevent so much of the clogging up, and then we have designs based on water pressure, similar to the kinds of speed sensors that you have on aircraft.
Okay, thank you. Have you tried using beaver deceivers? Maybe you could just say what that is. I don't, perhaps others don't as well.
Have I tried using beaver what? Sorry?
A beaver deceiver. Somebody asked about that.
I don't know what that is
somebody...
either.
Okay, so
okay.
that's because beavers rebuild their dams primarily due to the sound of running water. So if there's a bit that's collapsed halfway through it or something, they will repair it. They don't really like the sound of running water. So what you do is you submerge a pipe below the level of the height of the dam to a point that you would want to have a sort of a drawdown effect, and you have the other end of the pipe below the surface of the water into the receiving watercourse. So there's no sound of running water. And what it will do is it will keep continually draining the dam faster than the incoming water, so that you will, to some extent, always have freeboard.
Fascinating. I think that sounds like one for Archie, who's running that. But they are amazing animals, and that sounds like a fascinating way to manage what they do.
There's a question about the use of LiDAR. How well defined are the channel profiles from the LiDAR sensor, both in the dry section and below water?
We tend to do the LiDAR work when the water level is low, because we have a very detailed profile above the water, and then if there's water in the channel, then we can't use the LiDAR below water, so we have to do that manually. So we do it at low water, and the cross sections are very well defined, so long as there's not too much vegetation. So we do have to chop away at the reeds when we do a cross section, and where we've done repeatability studies, taking a number of sections in the same place, they are very repeatable. Well, they're within 0.3% coefficient variation.
Okay, thank you. What are your plans for developing flow sensors and for future development of the level sensors?
So I think I've probably covered most of that already, but it's largely around around different types of technology to attack the same problem in different circumstances. So on bigger rivers, the sonar sensors are really good because you can just pop them under a bridge and you don't have to install anything in the river, and much easier to get permission for. On small rivers, they tend to get affected by weeds, and so we're working with pressure sensors to resolve that problem.
Okay, thank you. Caitlin suggested I highlighted something to you, and I think reading back in the chat, it was a comment that Ian Davis meant that the RA, there's a potential for the RA to raise farm profitability, and which means it has a negative cost in the long term. Is that you have found or aware of or could comment on? Sorry, yeah, I don't know what RA is. Perhaps you could explain.
Regenerative agriculture. So,
okay.
You know, my expertise is in the hydrology of regenerative agriculture. I don't know about the economics of it, but I have certainly read that in certain situations it can be more profitable in the long term. In others, I've read that it isn't. I think it really, you know, it really depends on, like everything, on geographical context. What's your soil like? What are you growing? Are you on the slopes? And all these other questions that are so site specific. And that's why, of course, we use spatial modeling when we're trying to investigate some of these processes.
Okay, thank you. Quite a technical question now, I guess, about Arduino sensors. Asking if your sensors are the same as those, and could you please explain the limitations of Generation 1 Arduino sensors?
Sure. So we started with Arduinos, but the particular problem with them is that they have very low program memory. So you can't do very sophisticated instrumentation or many multiples sensors on the same device. There are many flavors of Arduino, of course, so it really depends. They are quite consuming of power, so they're not very good in a low power environment like the field. They're great if you're just plugging them into a USB port on a computer, but in the field they're not very good. And secondly, thirdly, they don't have a watchdog, which ensures that if something goes wrong, they will reboot. Now, most microprocessors have that, and without it, it means they just hang if something goes wrong, which you might not know about till you revisit the Arduino 3 months later.
Okay, thank you. And probably, unfortunately, the last question we'll have time for, but perhaps a good one to finish on, is what do you think are the key remaining challenges in implementing NFM in the UK?
I think we still have quite some scientific challenges to evaluate NFM and different types of NFM in different contexts to really understand its role. I think there are challenges in understanding the long-term costs of NFM, both opportunity costs, but also maintenance costs and so on. And I think the third challenge is probably around the modeling required to understand the scales at which we're going to have to implement NFM to make a difference at over significant areas.
Okay, well, thanks very much, Mark, and thanks for your very succinct, clear answering of a large number of questions. So yeah, that's all we've got time for, I'm afraid. Just to finish, if your question wasn't answered, apologies, but please do get in touch with Mark. You can see his email address there. If you've got questions or would like to make comments, give us feedback on the webinar program or other matters, there's our contact details as well. The recording will be available on the website. I shared the link to that earlier. I'll copy it again into the chat shortly, alongside Mark's slides. The next webinar is on the 15th of April, and so this is a webinar from the research programme, the Landwise project, and Professor Keith Morrison and Dr. Will Maslanka from University of Reading will talk about improving soil moisture estimation from space radar. If you haven't signed up already, please do sign up to our newsletter. So it's roughly quarterly, to give you updates on our research work, and also we include articles on partner initiatives. And if you are signed up to it, we'll also update you on upcoming webinars. So it just remains for me to thank Mark for excellent presentation and answering of questions. Thanks very much, Mark, and also to Caitlin for answering a lot of questions on the chat, and to all of you for joining us. Hope you enjoyed it, and you'll join us again next time. So thanks again, and good afternoon.
Thank you.
Thank you.
Thank you.